Today we are continuing section 9.3 closed graph operator, and now we are going to discuss about theorem 9.3.4. Listen carefully. We have let x0, x1, x2 be Banach spaces and let t1 from x0 to x1 and t2 from x0 to x2 be linear map such that domain of t1 contained in domain of t2. Okay, and T1 is a closed graph operator and T2 admits a closure. Then there exists a C greater than 0 such that norm of T2x less than or equal to C into norm of T1x plus norm of x for all x belongs to domain of T1. So we have to prove this. Okay, and given that T1 is a closed graph operator and T2 admits a closure. Just recall what is meant by a closed graph operator. An operator A is called closed graph operator if gamma A is closed set in x cross y. What is gamma A? Gamma A is set of graph of A, that is set of all x AX such that x belongs to domain of A. And another form is xn belongs to A is a closed graph operator implies xn belongs to domain of A, xn converges to x, axn converges to y, then x belongs to domain of A and the ax is equal to y. So to prove A is a closed graph operator, we have this result. Or if A is a closed graph operator, we have this result. If xn belongs to domain of A and xn converges to x, axn converges to y, then x belongs to domain of A and ax equal to y. Now what is the meaning of A from x to y admits a closure? We are using this result actually. If axn converges to y, xn converges to 0, then this implies y equal to 0. Okay, so we are using this result in this theorem. Okay, so we are moving to the proof. Consider the closed subspace E equal to set of all x t1x such that x belongs to domain of t1. Okay, what is E? E is equal to set of all x t1x such that x belongs to domain of t1. What is this actually? This is actually a graph of t1. So clearly it is a subset of x0 cross x1. Okay, here x0, x1, x2 are Banach spaces. Okay, T1 is a closed graph operator. T1 is a closed graph operator means gamma of T1 is a closed set in x cross y. Here gamma is a closed set in x cross y. That means here gamma T1 is a closed set in x0 cross x1. Therefore, this subset, this E is actually a closed subspace of x0 cross x1. Okay, the closed property is from the definition of T1 is a closed graph operator. Okay. Now we set V of x T1x is equal to T2x. We set V of x T1x is equal to T2x. Now we are proving V is a closed graph operator. V is a closed graph operator. But we have to prove this. T2 admits a closure and we have to prove this. Okay. So here what we are going to prove is we know what is T2x. For any x, what is T2x that we know. Okay. And for any x, what is T1x that also you know. And we are defining a function V from actually x T1x is from E. So V is actually a function from E to x2 because T2x is, where is T2x? T2x is in x2. Okay, now we are proving, we are claim V is a closed graph operator. Okay, to prove V is a closed graph operator, what we have to prove? We have to take an element in E, take a sequence in E, and if that sequence, let that sequence be some xn converges to x and vxn converges to y implies X belongs to domain of A, domain of V, and we have to prove Vx equal to Y. Now we have to choose Xn in E. What is the set E? E is actually a collection of all ordered pair. So we are choosing an ordered pair. Here E is actually Xn T1 Xn. So we are choosing a sequence Xn T1 Xn, and that converges to some point. Okay. And that point also be in ordered pair. Let that ordered pair be XY. And this Vxn, that means V of that sequence converges to, as we have used Y here, we are denoting the limit as Z. Okay. So for convenience, we use limit as Z, and we have to prove V of X equal to Z. That means here we have to prove we have to prove V of XY equal to Z. If we prove V of XY equal to Z, then V is a closed graph operator. So what we have? We have xn t1 xn converges to xy. What is the meaning of xn yn converges to xy? What is the meaning of that? This implies xn converges to x and yn converges to y. Therefore, xn converges to x and t1 xn converges to y. Now T1 is a closed graph operator. Therefore, Xn converges to Y, T1 Xn converges to Xn converges to X, T1 Xn converges to Y implies X belongs to domain of T1 and T1X is equal to Y. Okay. We have assumed Vxn T1xn converges to Z. What is Vxn T1xn? Vxn T1x is actually T2xn. So T2xn converges to Z. T2xn converges to Z. Now what about T2 of xn minus x? T2 of xn minus x is actually T2 of xn minus x is equal to T2xn minus T2x. What is T2xn? Z minus T2x. Now T2 of what is xn minus x? Xn converges to x implies xn minus x converges to 0. T2 admits a closure. We have an operator A admits a closure means Axn converges to 0. Axn converges to y. Xn converges to 0 implies y equal to 0. So here T2 xn minus x converges to z minus T2x and xn minus x tends to 0 implies z minus T2x. For y we have z minus T2x. This equal to 0. That means T2x is equal to z. What is T2x? Vx T1x is equal to z. But we have T1x is y. Therefore Vxy equal to z. T1x is equal to y. Okay, so this actually what is xy? Xy is actually x t1x. Therefore, this is clearly belongs to E. This implies xy belongs to domain of t1. Sorry, domain of V. Therefore, xy belongs to domain of V and V of xy equal to z. That implies V is a closed graph operator. Now, what about domain of V? Domain of V is actually graph of T1, that is E. So, by closed graph theorem, V is a continuous function. Because what is closed graph theorem? The closed graph theorem says that let x and y be Banach space. It is not here. You just recall what is closed graph theorem. Let x comma y be Banach space A from x to y be a closed graph operator. Then A is domain of A equal to x. Then A is continuous. So here V is continuous. That is implies what is V is continuous implies continuous function on a bounded set. That means V is bounded. That means there exists a constant c such that norm of v of x t1x less than or equal to c into norm of x t1x. Now, what is v of x? T1x is t2x, which is less than or equal to. We have a norm of ordered pair xy is equal to norm of x plus norm of y. So, this is less than or equal to c into norm of x plus norm of t1x. Okay. Now we are going to discuss one example. For any x belongs to C2 0, 1, that is for any twice continuously differentiable function on closed interval 0, 1, we have a norm of x dash is less than or equal to m into norm of x double dash plus norm of x, where this is a norm on the space C0, 1. So this is actually, we are applying this result, theorem 6.3.4 for the set C201. Okay. So here we are choosing x0, x1, x2 as C01. Sorry, we are using this one C01. So what about T1? T1, we define T1 as second derivative. Okay. And T2 as first derivative. So what is T1? T1 from x0 to x1 defined by T1x is equal to x double dash. Therefore, this is twice continuously differentiable function. And the T2 from x0 to x2 as T2x is equal to x dash. That means differentiable functions. So domain of T1 is actually C2 C01, which is completely contained in C1 C01, which is equal to domain of T2. So domain of T1 is contained in domain of T2. And T1 is a closed graph operator, because we have already discussed in example differential operator is a closed graph operator, therefore it also admits closure. So T2 is also a closed graph operator, therefore T2 admits its closure. Therefore, by above theorem, there exists a constant m such that norm of t1, t2x, that is t2x is first derivative norm of x dash less than or equal to m into norm of x plus norm of t1x, that is second derivative. Okay, hope it is clear. Now moving to last theorem. Let E1 and E2 be closed subspace of a Banach space with E1 intersection E2 equal to set 0 and E1 plus E2 equal to X. Then the projection P from X to E1 parallel to E2 is a bounded operator. In other words, there exists a C greater than 0 such that C into norm of x1 plus x2 greater than or equal to maximum of norm of x1, x2. For x1 belongs to E1 and x2 belongs to E2. So we are going to prove this, and we have P is from x to E1 is a projection map and it is parallel to it. Okay. So what we have to prove? We have to prove this result. For proving this, what we are going to prove is we are proving projection. This projection is a closed graph operator. Okay. For this, what we have to take? We have to take a sequences to prove P from X to E1. Okay. Here I have written projection, the definition of projection. Let E1 is equal to image P, E2 is equal to kernel P. Sorry. Here we have this result. E1 is equal to image P, E2 is equal to kernel P, E1 plus E2 equal to E and E1 intersection E2 equal to 0. Then P is called projection onto E1 parallel to E2. Okay. So what we are defining is P, suppose x is equal to x belongs to E, and if we write x is equal to x1 plus x2, Then we define Px is equal to x1. Okay. So here what about, here P is a function from x to e1. We have to prove P is a projection, closed graph operator. For this, we have to take a sequence xn in x such that xn converges to x, pxn converges to y, implies x belongs to domain of P and Px equal to y. Px equal to, this is what we are going to prove. So here to take a sequence xn, as xn belongs to E and E is equal to x, xn belongs to x and x equal to E1 plus E2, you can write this as a sequence. Okay, xn is equal to x1n plus x2n. Okay, and we assume that xn converges to x. And this projection, what about projection of xn? Xn, pxn is actually x1, and suppose pxn converges to x1, that is x1n converges to x1. Then what we have to prove? We have to prove px equal to x1. Okay, so we are proving, what we are going to prove is, we are proving x, first we are going to prove x2n is convergent. Okay, here x1n is already we have x1n is converges to x1 and xn converges to x. So norm of x2n minus x2m is equal to norm of, we are adding x1n and subtracting x1n. Then adding x1m and subtracting x1m. And we are rearranging this in the order n x1 x2, m x1 x2. Okay. So this is actually x1n plus x2n, that is xn. This is also, this you can write as minus x1m plus x2m. And this is actually, this is equal to minus xm. So xm plus x1m minus x1n. And this norm is less than or equal to norm of xn minus xm plus norm of x1m minus x1n. Xn is a convergent sequence, x1n is also convergent sequence. Convergent sequence are Cauchy, therefore this converges to 0 as m comma n tends to infinity. This implies x2n is Cauchy. X2n is a element in E2, E1 and E2. What about E1 and E2? E1 and E2 are closed subspace of a Banach space. Closed subspace are complete. Therefore, X2n is also convergent, and X2n converges to an element in E2. Suppose X2n converges to X2, and we are claiming X is equal to X1 plus X2. Now, what about norm of x1, xn, for proving this, what about norm of xn minus x1 plus x2? We are just adding x2n, we are replacing xn by x1n plus x2n. So, this you can arrange as x1n minus x1 and x2n minus x2. This here you can write as norm of x1n minus x1 plus x2n minus x2. Okay. And this is less than or equal to triangle inequality, as x1n converges to x1 and x2n converges to x2. This norm also tends to 0. From this we get xn is converges to x1 plus x2. But we have xn converges to x. Limit of a sequence unique implies x is equal to x1 plus x2. Okay, so where is x1? X1 is in E, x2 is in E2, x1 is in E1, x2 is in E2. So x1 plus x2 is in E. Now what about px? Px is equal to x1 And what about domain of P? Uh, okay, px is equal to, so what about what we get? We get px is equal to x1. So what we have? We have xn converges to x. Uh, pxn converges to x1 implies px is equal to x1 and x is in domain of P. Here px is equal to x1 and clearly x belongs to x is equal to x1 plus x2. x1 is in E, x2 is in E1. x1 is in E1, x2 is in E2 implies x belongs to capital X and that's equal to domain of P. This implies P is a closed graph operator because domain of P is also equal to X. And by closed graph theorem, we have P is a bounded operator. Therefore, there exists a m greater than 0 such that norm of Px less than or equal to m into norm of x. Norm of Px less than or equal to m into norm of x. But what is norm of Px? Norm of x1 less than or equal to m into norm of x is norm of x1 plus x2. Okay. Using the same argument, we can apply this result to I minus P. We know that Q equal to I minus C is parallel to E1. And this implies using same argument, we get Q is a bounded operator. Therefore, there exists a M1 greater than 0 such that norm of Qx less than or equal to M1 in norm of Qx less than or equal to m1 into norm of x. But what about q? I minus p x is actually x2. So this is norm of x2. You can refer uh, chapter 6 for the operator I minus p and more details about I minus p. M1 norm of x. So what we have? We have norm of x1 is less than or equal to m into norm of x1 plus x2 and norm of x2 less than or equal to m into m1 into norm of x1 plus x2. So here if you choose capitals or C as maximum of m1 m2, what we get clearly norm of x1 is less than or equal to C into norm of x1 plus x2. Similarly, norm of x2 is less than or equal to C into norm of x1 plus x2. Okay. We have some norm of x1 is less than or equal to some 7 into norm of some y. Norm of x2 is less than or equal to some 9 into norm of y. Clearly, if you choose 9 or 10, clearly norm of x1 is less than or equal to 10 into norm of y. And similarly, norm of x2 is less than or equal to 10 into norm of y. So x1 less than or equal to x2. That means maximum of x1, x2 less than or equal to 10 into norm of y. Therefore, maximum of x1, x2 also less than or equal to c into norm of x1 plus norm of x2. That's what we have to prove. Okay. So what we have proved today, we have discussed two theorems and one examples. First theorem, theorem 9.3.4 and some example. Then theorem 9.3.5. Hope it is clear. That's all for today's class.